Eric Dollard, everybody.
Okay, so let's roll. Basically what this is like a culmination of all my past presentations. So that provided all the theoretical basis and proofs and types of math and what have you. So I'm going to be more at an engineering level directly this time. The objective is to see if we can get Wardenclyffe to run. So we're not going to start with the theory, we're going to start with the realization. So we have to establish our engineering objectives. What is it we want to build at Colorado Springs? And the objective is the propagation of electric power via the polarized electric medium bound by the physical mass of the Earth. It's kind of a mouthful. What is the electric medium? Good question. You have to go back to your ether presentation for that one. But in Tesla's mind, it was a very ultrafine gas, or what I've called in my past presentations, a Mendeleev pre-hydrogen inert gas. And Tesla and Crookes had absolute certainty in their minds that this existed, and Tesla engineered it. So we want to propagate power through this. Well, how are we going to do that? Well, that's why we're going to build Colorado Springs. So now we have to establish what Tesla called a stationary wave, the radio people called a standing wave. We're going to stick with Tesla's terminology as much as we can through all this. And we have to make this wave in the Earth with the unipolar transformer. And then this standing wave sets up nodal points on the surface of the Earth, and then we connect the receiving transformer there, and that is the way that electric power is carried from one point on the surface of the Earth to another point on the surface of the Earth, is through the nodal points created by a geometric stationary wave pattern, which we'll see diagrams of later, that exist inside the Earth. That gets to be a very deep subject, as we'll find out. Everything pretty much here is going to be what Nikola Tesla said or tried to get across to people that didn't want to hear it, but he was persistent. So this is one of the best articles, The True Wireless in the Electrical Experimenter. I think this is the 1919 one, but this has a lot of important material in it, and it needs to be paid attention to. So a lot of people have seen this picture, but I don't think a lot of people know what all this stuff is in it. But this is the final development. So let's identify. So in the red, we got the big secondary coil. The primary's down on the floor. And then the tanks, which contain the Leyden jars. Well, let me go through the steps here. So the secondary, by the regulating coil, if you look closely, you can see there's kind of a handle on it. That's his tuning inductance. That's how he sets his frequency. There's an adjustable capacitance. That's the brighter yellow. You can see all those knobs sticking up out of one of the tanks. There's two of those tanks. That's how he switches the individual Leyden jars in and out to get the final capacity. So that part of the setup there, the coil and the knobs on the capacitors, that's his frequency control. Now what we're going to do is we got to build a scale model of it. So let's begin that process. It's not as easy as it sounds. So we're going to make it 1/20th. Turns out to be, if I made it 1/40th or 1/30th, the scaling factor collapses on itself. Same thing like in the musical scale, and that's why you need equal temperament. That was a complication. It always turns out to be complications when you do this stuff. If I went 1:10, which would land it on a new ham radio experimenter band where this thing has actual application as a communications device, then it's too big. I couldn't fit it in the back of my car. So it had to be 1:20, and where did that land me? Right where I didn't want to be, right smack in the middle of the AM broadcast band. But then what came out of it was, well, let's use it as a crystal radio and receive AM. So we kind of fudged that a little with a regular radio, but I think it was evident that the amplitude was much greater when the ground was connected. Okay, so scaling factors. So 1 to 20 is 0.05. But you can't scale everything that way because the wire is not based on linear dimensions, it's based on square dimensions. So you end up with a sectional scaling factor of the square root of 1 to 20. And that allows everything to still work out within a boundary set of limits that the scaling allows. And here's this is the extra coil, the turns and the spacing and a number of the measurements that were done on it. This will all be in the PowerPoint later, so I don't have to really pick at a lot of stuff here. And these are the resonance tests that we did. So this is the reactance chart as we go from a lower frequency to a higher frequency. And the dielectric is when the reactance is, or the green is when the reactance is dielectric, and the red is when the reactance is magnetic. So obviously at the resonant point, which is the dotted line, they cancel each other out and the reactance is 0. You're only left with the resistance. This is with the mast. So in this case, the extra coil is not operating as a distributed coil for the most part. And it's actually trying to operate as a regular coil and the mast as a capacitor, and this was Tesla's intent. Tesla was trying to get rid of the distributed constants, and all he wanted was an LC circuit, which may have been a false path, but that was his objective. Whether it was right or wrong, but it's my belief that you have to have the distributed constants to some extent before the thing can transmit longitudinally. And so these are the things that have to be preserved when you go from one system to another in scaling. The percent luminal velocity has to be the same. The natural impedance has to be the same. The inductive reactance has to be the same. The magnification factor has to be same, and the propagation constant has to be same. Good luck. Well, let's give it a shot. Okay, so this was my first page after hissing at Tesla's notebook for a week. I finally forced this into existence and had to implement equal temperament in the primary secondary and kind of worked it out. So then this is what's out there on the floor now. This is Bruce Gavin's drawing that he sent me. And this is what's on the floor as far as the extra coil goes. The extra coil, the only problem with the scaling on the extra coil is the wire comes out to be a lot thicker, and we had to fudge the spacing and the length of the coil a little bit so the wires wouldn't touch each other. So here's the construction process. So you've already seen most of these things. That's the extra coil. That's its mast. And this is there in the process of being put together mechanically. And then the dielectric spacers go in for the conductors. The primary form gets bolted into place, and then the windings get put on, and we have the finished product. So let's try to come up with the coordinate system. Well, I did that in one of my presentations. This is the title cover page of the presentation. It was quite an ordeal. It's all mathematics, but nevertheless, it's a good preamble to what we're getting into here. So if you want to get more in depth into this is the presentation you want to watch. This is the one that basically eradicates velocity from the equations and allows for a more longitudinal approach. So if we have one turn of the coil, we have complex magnetism. Maxwell's equations are useless here. We're dealing with a quadrature magnetism where we have two magnetic fields. We have the magnetic field of mutual induction, which surrounds the turns, and we have the magnetism of self-induction, which is in between the turns. A lot of experience in doing this type of stuff. Most of it came out of my experiences at RCA Bolinas. I produced a book on it, which is not a book yet, but it is a digital thing. And this is my Bolinas work. This is the building number 1 grounding system. The building is 100 by 100, so that's a lot of ground. The original blueprints of the Bolinas installation were embezzled from me by the people, same people that always did that. I won't mention their names, but you would know it if I told you.
More questions?
Guess that's it.
Okay, and before we go, I have a few announcements, but hey, Eric Dollard, thank you. You should give yourselves a round of applause because I think this is the largest audience who made it this far in a 4 to 5 hour Eric Dollard presentation.